Hi everyone, welcome to the IoT Show Deep Dive. Today we are going to talk about getting started with Azure RTOS. And if this is your first deep dive you've gone to, we're really excited to have you here. We're actually going to have a bunch of different technical walkthroughs. We'll actually go through every single Azure RTOS component. That way you can see what the different components do, where to get the samples, and how you can get started with each one of them. And because this is a deep dive, it means that we would love to hear your questions so we can answer them in chat. So feel free to join in on YouTube, on the chat, ask your questions. We'll be there to answer those. And if you are viewing on demand afterwards, don't worry, you can still reach out to us through Tech Community, and I will give you that more information at the towards the end of the deep dive. So let's go ahead and get started. I am super excited that we have Scott here from the Azure IoT team. Scott, do you want to give a little bit more information on what you do here?
Sure, thanks, Pamela. I am Scott Larson. I've been with well, before joining Microsoft, I was with the whole team that designed Azure RTOS. So I've been working with this team for about 7 years now, and I'm a senior software engineer at Microsoft.
Awesome. Well, thanks, Scott. I'm super excited to have you here. My name is Pamela Cortez. I am going to be your host for today. I'm also on the Azure IoT team focusing on developer community and training. So let's go ahead and jump right into it. So for the agenda today, there's a couple different things that we're going to go into. One, I'm just going to give a quick overview of our training resources, just because I'm getting a lot of really great questions on what's next on if I really want to dig into all of these components. Where can I go to train? So I'm going to talk about that, and then Scott, he's going to be going into the intro and then deep diving into each one of the components. So our training roadmap, as I mentioned before, we had an IoT show episode. Think of that as if you've never even heard of Azure RTOS, that is what to watch. That is a great episode for you to learn about real-time operating systems and just understand what our offerings are there. And then our partnerships with different partners like NXP, ST, Microchip, and how we are working with them to build this ecosystem out. In June, which is this month, we have our deep dive on not just Azure RTOS, but also the embedded C SDK, where we talk a little bit about the convenience layer that works with Azure RTOS. And then for July and August, this is when we're going to have even the more training videos to help support. And we're also up ramping on our getting started guides as well. So just wanted to showcase that, so that way you know what's coming up in the future and some resources that you can use to really understand on how to build an application with Azure RTOS. All right, so I'm going to go ahead and hand it over to Scott. I'm your host. What I'll be doing is answering questions in chat, and I'll also be asking Scott some questions, throwing him some curveballs, but hopefully no super tough questions, but I'm pretty sure Scott can handle it. So let's go ahead. Scott, do you want to go ahead and talk about Azure RTOS and jump into the different components?
Absolutely. Yeah, let's get started. So Azure RTOS is composed of, well, I mean, these are 6 components here, but it's really only about 5 of these. Obviously, we have ThreadX, which is a real-time operating system kernel. So everything runs on top of ThreadX. So we've got NetX and NetX Duo are our TCP, IPv4, and IPv6 stacks. Really, I'm just going to focus on NetX Duo, which is obviously a dual IPv4 and IPv6 stack. And then next we have GUIX and GUIX Studio. And that's basically a complete user application design environment, and then a lightweight graphic stack that runs on the target. Next, we've got USBX, which is a USB host and device stack. And then FileX is a FAT12, FAT16, FAT32, and exFAT file system. And then TraceX is another component, but it doesn't really run on the target. It's a It's an event trace tool that is really helpful for analyzing and debugging your multi-threaded application. So first, we're going to just jump into ThreadX because that's kind of the whole foundation of everything here. So ThreadX provides all the basic RTOS services. If you've ever used a real-time operating system before, you're probably familiar with threads. Some operating system called these tasks, and then we've got mutexes, semaphores, event flags, queues, and block and byte pools, and timers. And there's a few different ways you can do scheduling. ThreadX is naturally a priority-based, preemptive, multi-threaded scheduler. But you can also do cooperative scheduling, round-robin scheduling, and time slicing. So you can, threads can cooperate and naturally relinquish control to other threads. And then round-robin and time slicing are more time-based. Each thread can have X number of milliseconds or X number of ticks that they run in, and then a new thread gets scheduled. And we have some let's call them advanced features of ThreadX, like preemption threshold. So you can actually set different thresholds for different threads for the priorities that they can be preempted. So it's like a neat way to let super high priority threads run, or let super high priority threads interrupt lower priority threads. And we can get more into that later. Actually, there'll be future videos that go really in depth with exactly how and why you would want to use these things. And then ThreadX also supports multi-core processors. So we have ThreadX SMP, which is symmetric multiprocessing. So you'd run that on homogeneous cores like a dual-core Cortex A9 or a quad-core Cortex A53. And you can also just run normal ThreadX and your normal application on multiple cores. So that would be AMP mode, asymmetric multiprocessing. For example, if you've got like a Cortex A7 and a Cortex M4, you can run basically two completely different applications on each of those, but they could both be running ThreadX. So there's also a little add-on, if you will, to ThreadX called modules. And modules takes advantage of the hardware MMU or hardware MPU, basically the memory management unit or memory protection unit. You can think of modules kind of like processes where each module can contain one or more threads, and you can have one or more modules. And the kind of the main application can load and unload modules dynamically. You can load them from, for example, a USB flash drive, or download them over an internet connection, or load them in and out of, SPI flash memory, for example. So these are just unique ways to maybe add or remove functionality from your application, or execute third-party code, or just use these to take advantage of the memory protection features that the processor provides. So next, we're just going to get into a little super basic kind of how your application starts. So the basic ThreadX structure here. In any files that you're using the ThreadX API, you would just include txapi.h. And this is all just standard C code and standard C header files. In your main function, you would probably set up your processor, maybe set up your hardware. And then at the bottom of main, you'd call txkernel enter. So that's what actually enters the scheduler. So you don't actually enter ThreadX or the scheduler until you get into main. So all the startup code, anything you entered before main, or any hardware setup, you can do all that. ThreadX doesn't really care what bootloader you use because it doesn't start running until you get into main. So any bootloader you use is fine. So once you call txkernel enter, ThreadX basically initializes all of its data structures, and then calls this function tx application define. And it passes the first unused memory location into that. So this is where you can begin creating ThreadX objects like threads and mutexes, etc. And with the first unused memory parameter that it gives you, that's basically a pool of unused memory that you can use for your application. You can also, statically create memory. So you create all your objects in here. You can also create objects dynamically, but typically, a lot of applications create their threads. Those threads run. But yeah, you can also create everything dynamically. And then at the bottom of this file is my thread entry. So that would be the entry function for the thread you've created. And every thread is basically just an infinite loop. I mean, if you're gonna, if a thread is gonna continuously run, it's typically an infinite loop. And all this thread does, to keep it really simple, is it increments a counter and sleeps for 1 tick. So that's just a very, very, very basic intro. So now I would like to actually show a real example. And for this, I will bring up Firefox, or bring up my browser and try to share my browser screen. All right, so this is a demo that we have on GitHub, so anybody should be able to access this. It's in ThreadX samples demo_threadx.c. And this is basically an example that creates 8 threads and a queue, a semaphore, a mutex, event flag, block, and byte pool. So it kind of just shows everything, all the different objects you can create, except for timers, and kind of how they interact. So all we've done here is create a timer for each thread. These are just function prototypes for the thread entry functions. But as you can see in main, all we do is call txkernel enter. And then in our application define function, so this is much bigger. This is where we first we create a byte pool because every thread needs a stack. So then from this byte pool, we will allocate a demo stack sized pool, or so that would be, or the stack size is like 1,000 bytes, I think, or 1024 bytes. So we'll allocate a stack, and then we will allocate we'll create a thread. And we're going to do this 8 times: byte allocate, thread create. So we'll create 8 different threads here, and then we'll allocate a small section of memory for our queue, and we'll create a queue. We'll create a semaphore, create an event flags group, create a mutex, and then we'll actually do something kind of unique here. We'll allocate some memory to create a block pool, and then we'll just to show block pools really quickly, because we don't actually use them, we just allocate a block and then release the block, and then we don't really ever use that pool again. So let's look at all the different threads. So thread 0, every thread just increments a counter, and then this thread will sleep for 10 ticks, and then all this thread does is set a flag. And I'm actually not going to go in order of the threads. I'm going to go down to thread 5, because in thread 5 you'll see thread 5 kind of interacts with thread 1 in that it tries to get this event flag that thread 1 sets. So that's all it does, is it will wait for that flag. So now let's go back to thread 1, or sorry, thread 5 interacts with thread 0. So in thread 1, we send a message to a queue, and in thread 2, we will receive a message from the queue. So those thread 1 and thread 2 interact with each other. And then this is a pretty neat feature. Threads 3 and threads 4, or thread 3 and thread 4 both use the exact same function. So they both execute the same code. And they will get and put a semaphore. So it's just really neat to see them both interacting. And this is really cool when you actually trace through the code, step through the code. And I think we'll have a future video where we actually step through this code and show what everything is doing, or maybe we use a different example. Thread 5 we talked about, that just gets the flag that thread 0 set. And then just like threads 3 and 4, threads 6 and 7 interact with each other. They use the same code, and they both set or they both get a mutex and put a mutex. So yeah, this just shows all of the. It's just a good little ThreadX example, and we'll have future tutorials about ThreadX modules and how to use those. But we've got limited time here, so.
Yeah, thanks, Scott. Before we move on to the next component, to kind of add on to what you were saying with additional training, when we do the training videos for ThreadX, we used to do all of these boot camps, 2-day boot camps in person, and now we're going to have that virtually. So really think of this deep dive as giving you, getting started with these different components, but the additional videos will be able to deep dive even further on, the ins and outs. For example, ThreadX, for the future training videos, we're really going to cover that hello world application when it comes to, the basic concepts, but also thread services, memory management, and system timer. So just keep that in mind. And I had a couple questions, Scott, before we move on. One is, I know that Azure RTOS is really great for constrained devices like medical devices, but I'm wondering, what is that minimum footprint that ThreadX component has when, for example, maybe on a Cortex M or something?
Yeah, so for a Cortex M device, ThreadX itself only takes up about 2 kilobytes of memory. And then it really depends on how many different resources your application uses. For example, if you're using threads and mutexes and semaphores and block and byte pools, the footprint will grow a little bit. But if you are not using certain services, they won't be included in your code. So you won't have any excess bloat there. So yeah, the minimum footprint is about 2 kilobytes just for the ThreadX kernel, and that can grow up to about 20 kilobytes if you're using every single service. And then I can give you some estimates about the rest of the components as well, if that's something you're interested in.
Yes, and I'm also very interested in the device to cloud. What would that footprint look like?
So that would use NetX Duo, and NetX Duo takes anywhere from about 13 to about 40 kilobytes. So you can really, in about 50 kilobytes of code, you can connect your device to a cloud. Okay,
perfect. And then a couple more questions. So what if you really want to put your processor, maybe put it to sleep for extended periods of time? Do we have that support right now, or it documented anywhere?
I'm not sure that that's documented anywhere right now, but we are working really hard to get, the various add-ons that we've created and all the other ports up on GitHub. But yeah, we have some low power code that users can use to, really it's up to the application developer to determine what peripherals they want to put to sleep and like what kind of sleep mode they want to put the processor in. But the code will help do some timer maintenance. So let's say you end up sleeping for a few seconds or a few minutes. When you wake up, you want to see if any ThreadX timers have expired. So yeah, we basically provide these, kind of like the ThreadX maintenance functions for low power code.
Okay, perfect. Other question that comes to mind is, we talked about Cortex M, but what about Cortex A or Cortex R? Like, what about those ports?
Yeah, so we have all those ports for Cortex A and Cortex R devices. We don't have them on GitHub right now as of today, but we are working really hard to get everything up on GitHub as fast as possible. I think what's up there today is only Cortex M devices for GCC tools, but we also support IAR tools,
Okay.
ARM tools, and a few other tool chains. So, keep your eye on GitHub because new things are being put up every day.
Okay, perfect. So the support is there. It's just not on GitHub at the moment. So let's go ahead and jump into the next component because I know we have a lot to cover.
Super. All right. So next is NetX Duo, which is our TCP IPv4/IPv6 stack, and we support a ton of different protocols. This was all developed in-house. It's no open source code is in here. Well, I guess it's kind of available now, but when we developed it, it was all done to integrate as tightly with ThreadX as possible. So we started from scratch, and this is designed to be as high performance as possible. So for example, we'll take advantage of whatever features the hardware provides. Usually the hardware does some sort of checksum offloading, so the hardware will automatically calculate checksums, and we try to do zero copy. So basically when a packet comes in to memory, we will use that memory rather than copying the packet from the hardware into a whole separate memory packet. So that way we get pretty close to line speed. For example, on like a Cortex M device, they typically have 100 megabit per second Ethernet ports, and we're operating at like 95 megabits per second. In terms of protocols, all of these various protocols are supported. There's probably more now. And the IPsec and the secure DTLS and TLS are only supported in NetX Duo. They are not in the older IPv4 NetX product. So if you're starting a new design, I would strongly suggest NetX Duo. If you are connecting to a cloud using MQTT or CoAP or lightweight M2M, you'll pretty much have to use NetX Duo. And I think you'll find it's a lot more full-featured than the older NetX is. We're going to just show a super quick example here. Basically a little HTTP example. All right, cool. So I just wanted to share this NetX Duo HTTP example. This is up on GitHub. In fact, all of the examples I'm showing today are up on GitHub, and it basically we include TX API, we include NetX API. This also uses FileX. It actually doesn't have to use FileX, but because it's a HTTP server, it's serving files. So FileX is integrated in this as well. And then NetX Duo is an IPv4 and IPv6 stack. So we have options to enable and disable those as well in this example. This example doesn't actually use any real hardware. It uses a RAM driver, so you can. It's a good way to test that things are working on your system without actually having it connect to the internet and having a network available. You can basically run both this HTTP client and server on your device and just use this RAM driver. So the RAM driver comes with NetX. This should be one of our examples. And we actually have a FileX RAM driver as well. And we create a client thread and a server thread. This is just a little authentication function. And then in our main function, as you can see, we call TX kernel enter. And in our application define function, is where we kind of set up the whole structure of this application. So we create a server thread, we initialize NetX, we create a packet pool for NetX to use, because NetX basically communicates using packets. We create an IP thread, or an IP instance, sorry, and that actually creates an IP thread as well. And that uses the RAM driver, and then you just, we can discuss those, all the rest of those parameters in a more in-depth video about NetX. And then we call TCP enable, we set up our IP addresses, and we create our HTTP server. And so that's the kind of the whole server side of things. And then we create our client thread, we create a packet pool for the client, we create an IP instance for the client, we enable ARP, and we enable TCP for the client. So now we have basically a client thread and a server thread that can communicate with the world. Here's our client thread. We basically format a FileX disk, if you will. Basically format RAM to look like a file system. We open that media, and then we actually create our HTTP client here, and set up an IP address. We enable ICMP. We enable IPv6. We set our address. So there's a lot of little things that need to be done. We start our client, and then we allocate a packet and actually send. We actually create an HTML page and send an HTML page, and put that or write that client, or write that packet to the client. And then we also get this client test.html page from the server. And then, this is a super simple example. So after we do all that, then we just delete the client, and we're done with that thread. And the server thread does something pretty similar. We enable IPv6, we set our IP address, sleep for a little bit to get everything, basically to get all the IP thread stuff going. And then we start our HTTP server, and then we just let the client send its HTML page and then get its page back from the server. So just a super simple example that shows kind of a neat little HTTP application. So are there any NetX questions?
Yeah, I actually have a couple for you. So you mentioned that you have NetX and then NetX Duo. So what if I only want support for IPv4? And I don't care about any of the other protocols. And it looks like both NetX and NetX Duo actually has that support. What would you really say is the difference on choosing either NetX and NetX Duo?
Okay, yeah. So NetX is an IPv4 only and supports a handful of protocols. NetX Duo is IPv4 and IPv6. Yeah. And NetX does not have any of the security functionality, whereas NetX Duo has all of the security functionality. And NetX Duo has all of the kind of the IoT protocols built in. So CoAP, lightweight M2M, MQTT. So if you're trying to connect to a kind of a more of a cloud or IoT device, you'd probably want to use NetX Duo. If you kind of have maybe a legacy application that's just a kind of a simple IPv4 application, and you're not necessarily connecting to a cloud, NetX might be the way to go there. I would strongly recommend using NetX Duo for everything. NetX Duo has all of the same functionality that NetX has, plus more.
Okay, and then you did just mention MQTT. What are the extra protocols supported? Could you show Is there a list somewhere that folks can go to see for NetX Dual, everything that's supported?
Yeah, I think I had that up, but I forgot exactly where that is now.
That's
in, let's see, in add-ons, if you go to GitHub, the Azure RTOS GitHub under NetX Duo, there's a folder called add-ons, and you'll be able to see all of the different kind of protocols we support. And MQTT is in there. There's an MQTT client code, and all the code is wonderful because it's typically one C file and one header file. It just makes life kind of a lot easier. And, there's not a whole bunch of super nested or super, what am I trying to say? Just, layer upon layer upon layer of files. So it's really, hopefully simple and easy to use. As a developer, I love it. Hopefully, all you developers watching love it as well.
Yeah, easy to find everything as well. Okay, so I remember you did mention driver and different drivers. Where would I be able to know what driver support we have for a particular chip?
Right. I'm not sure if there's a drivers folder yet. We do have some ports available. I'm not sure if we're putting drivers in there necessarily, or just kind of like the processor specific code. But under samples, we have, I know those are just different samples, but I think we've got 4 actual boards up on GitHub supported right now. And just like everything else, just like all the different ports, we're going to be constantly adding to that over the next couple of weeks and months, trying to get as many drivers and hardware development boards supported as possible. So if you don't see something up there, it doesn't mean we don't have it. If you contact us, we can give you a lot more information whether we actually have these things or not.
Sounds great.
We are,
yeah.
Yeah, we're also working with our partners closely, like ST and Microchip and NXP. We're working with them to get drivers built and make sure various development boards are supported.
And that's a great call out, Scott, on that. We're doing, once we Microsoft acquired Express Logic and ThreadX and all of the different components, we're trying to make all of this available on GitHub, these different resources and what the support is. So there's a lot of things that we're porting here. And so I like that call out of saying that, hey, keep checking what we have. Doesn't mean it's not supportive. We don't have, drivers or protocols or anything like that on GitHub at this moment. Just know you can reach out to us and that we will be updating. So I love that call out, Scott. So I think that's all the questions I had at this moment. So maybe we could jump into the next component.
Absolutely. So let me, let's keep going. Next is GUIX. This is one of our components that I find really exciting because you can actually see, you can actually see it. You can see what's happening. So GUIX, this is a lot of text up here, but GUIX is just a lightweight graphics stack. And then your user application can define its whole user interface using various GUI or various GUIX functions to create windows and widgets. And widgets are what we call all the different like buttons and lines and gauges and circles and all the different things you can create. GUIX is event driven, so events can come from widgets or external sources like timers and other internal sources. Touch screens are obviously an event, detecting a touch or a pen up or a pen down event. There's a GUIX thread that basically does all the drawing and refreshing the canvas. And we try to be really efficient about the way we draw things. If an area of the screen doesn't need to be redrawn, we don't. We only kind of redraw what we call the dirty areas or the parts of the screen that have changed. And we have a whole bunch of display driver templates that come with GUIX. And then if you're using a chip that has some sort of hardware accelerated graphics hardware in it, we try to take advantage of those. For example, the Renaissance Synergy chips have graphics hardware in them. The STM32 has Chrome Art. So we'll take advantage of whatever drawing capabilities that your hardware has. And yeah, we're constantly working on new drivers and different color depths. So yeah, GUIX is a really, really fun product. And then, that's just on the device itself. And then we have a product called GUIX Studio, which is a what you see is what you get design tool that you run on your host's operating system. For example, you'd run it on just your Windows desktop. So GUIX Studio basically just creates this XML document that has all the different elements of your user interface in it. So it's nice because you can share it with people. Multiple people can be working on the user interface, and the project files that are created in Studio are not needed for running on the target. It's just an XML file for Studio, and Studio will actually auto-generate all of the C code and header files necessary for your user application. So you basically design it, hit a button generate output files, and then GUIX Studio generates all of the code that your application needs to run on the target. So it's super convenient, super easy to use. You don't have to be building all sorts of little buttons and stuff, on your embedded, programming that stuff into your embedded device. You can do it all on the desktop. GUIX Studio is really neat. A ton of different languages can be supported, and you can use just about any fonts you want. You just have to make sure that the glyphs you are trying to use are included in the font that you are using. And then you can create custom themes. So, for example, I know everything lately has a dark mode now. So you can create a light mode and a dark mode that changes the colors and fonts and pixel maps at runtime. So yeah, GUIX is neat. So I just wanted to walk through a GUIX kind of a GUIX example really quickly. Here, let me. Oh, sorry. Yeah, let's just a quick slide about GUIX resources. There's GUIX creates or has a bunch of built-in predefined system colors, which users can modify. So you can kind of keep a color theme that you want. Fonts are created to a GUIX format font, and then pixel maps like JPEGs and PNG files are converted to a GUIX pixel map format. So basically, we kind of convert all these things to GUIX data types just to remain as optimized and fast as possible. Right, we're running on these really constrained devices, so we try to speed is everything. We try to be small and fast, and then resources are really easy to reference without any code changes. You can take a resource and change its color, change its font. And again, everything's auto-generated. So let's just quickly look at a GUIX example. Unfortunately, I can't zoom in on this, but this is just a little washing machine demo. We've created like a washer on, a water temperature, a water level. And what's really neat about these, all of these examples are included with, there's a whole bunch of different examples included with GUIX Studio, and you can download that from GitHub. And what's really interesting about these is you can also run them in Visual Studio. And there's all of these have project files that you can run in Visual Studio. So I'm actually running, or I just started one of our demos called the medical demo. And unfortunately I can't run it, or I can't zoom in on this. But this is basically a little GUIX window that Visual Studio popped up, and you can scroll through lists. There's, for example, these sliders, and then we've got this neat little kind of animation. GUIX also supports animations. So, before even running on an embedded target, you can run your whole user interface on your desktop and make sure everything works as expected. So yeah, it's a really cool product. So let's move on to USBX. So USBX is our USB host and device stack. We support a whole bunch of different classes, a whole bunch of different instances. It's also integrated with FileX and NetX and NetX Duo as well. So we have support for USB devices that might have multiple configurations, or composite devices. We also do USB power management, and then there's USB OTG, which is on the go. So we support that as well. And we'll discuss export trace events for TraceX. But basically all the different products, or all the different components, also are tightly integrated with TraceX. So you can see not only, well, actually, I'll discuss that when we get to TraceX near the end of the presentation. And then in terms of host highlights, we have multiple host controllers and then cascading hubs. So you can, USBX, we try to adhere pretty closely to or very strictly with, actually, the USB 2.0 specification. So, USBX can support up to 127 devices, and I think, like 6 or 7, cascaded hubs. I think you'll find you'll run out of memory on your system before you get up to 127 devices, but USB can handle it, or USBX can handle it. So let's just check out some of the classes that we support. On the host side, we support everything you see in the first 2 columns, and then device support is the last column, or the very rightmost column. And we are also working on developing new classes, supporting new video protocols. So if you don't see something here, that doesn't mean we don't have it. We are either still working on it, or if there's something you really want to see, feel free to reach out to us, because we want to build products that you want to use. And we actually have we've got a great example that shows you how to build your own device and host classes as well. And that's actually kind of the example that I wanted to show. So this example, again, is on GitHub. And if I bring up the example here, this is a depump example, or data pump, but it's kind of it's a really good template for you if you wanted to create your own USB class. Maybe you're trying to build a custom device where, kind of the device that doesn't really exist yet, or you just wanted to make a totally custom class that did something very unique to your application. I would start with this. But anyway, so we create a full speed and a high speed device descriptor. So we won't get into the specifics of USB today, but you have all these different the device and the configuration and the interface and endpoint descriptors. And then we just get into main. We call TX kernel enter. Application define is, again, where we set up our whole system. So we'll call UX system initialize. Initialize our host stack, and we'll register our class. In this case, we're registering the dpump class. And then we'll register a host controller. In this case, we're using a simulated host. What's just like FileX and NetX, we also have a USBX kind of driver that just is a simulator. It just runs in RAM. You don't actually need to start off using the real hardware. So let's say you don't have any drivers developed yet. You can still create a USB application. So this just hopefully makes development a lot quicker in that you don't have to wait for real drivers before you start actually developing your application. But we basically just initialize the device stack, register the dpump class, right? We're actually using both a host and device in this demo. And then initializing the simulated device controller. We're creating a host thread, and we're creating a device thread. And then in our host, we get the class that we're going to use. We're using the dpump class, and that's basically all we're doing is sitting in this loop, trying to talk to dpump instances or dpump devices. So once a dpump device is connected, then we get into our main loop where we will basically just talk to the dpump device. So we'll just write some data to it and read some data from it, and just kind of do that in a loop. It's a pretty simple demonstration. And then again, our device thread will sort of do the same thing. It will read from the host and it will write to the host. So super simple, kind of example where you can see both sides, host and device going. Yeah, that's really all I wanted to show for GUIX, or for USBX, sorry.
Thanks, Scott, for showing that sample. I'm curious on what is our driver support look like for USBX?
Great question. We have some drivers available on GitHub. If you go to the USBX folder and go to the common directory, you'll see we have some USBX host controllers. We have EHCI and OHCI. Those are probably the two most popular host controllers. And then for devices, it doesn't look like we have any device controllers up here yet, but we are working on getting them up here. So we should be able to support lots of the more popular microcontrollers. I know we've got drivers for ST, Renesas, NXP. So those are still trickling up on GitHub, but they, various drivers will be up there. If you don't see a driver, just ask us, and we're either probably developing it or working on it.
Okay, great. And you already asked or answered my other question, which is pretty much how many devices and hubs can connect to the USBX, which really sounds like it's a very large number. And really what's going to come down to is the memory available in your system.
Right. So yeah, USBX sticks very closely to the USB 2.0 specification. So it certainly can handle all of the possible combinations that you can connect to it. I think the bigger problem you'll have is your device probably won't have enough memory, and or your device won't have enough hardware endpoints in its actual USB controller hardware. So you're really limited. You're pretty much limited by whatever the USB hardware in your controller provides.
Yeah, that definitely makes sense. So those were my two biggest questions and the ones I've been hearing the most from developers, fellow developers. So let's move on to FileX.
So yeah, next up is FileX, which is a FAT file system, and all the different FATs are supported, 12, 16, 32, and exFAT. One really neat feature of FileX is its fault tolerance feature, and it's an optional feature that you can include or remove at compile time. But what fault tolerance does is it guarantees your file system integrity. So for example, if you have a sudden power loss or sudden reset, your file system won't get corrupted. And then the next time FileX starts up after that power loss or after that reset, FileX will try to it's basically a journaling system where it will try to restore the media to whatever state it was at before the interruption occurred. So this way we kind of maintain the integrity of the file system. And then there's a feature called LevelX, which is an add-on, and that's used for NAND and NOR flash wear leveling. I know a lot of people are using NAND and NOR flash memory. So LevelX just provides a way to extend the life of your memory. It's a pretty easy thing to use. We've got simulated drivers online for LevelX. Honestly, it's a really easy product to use on top of FileX. And if you're using flash memory, I would absolutely use LevelX. What's next here? I think I just wanted to show a quick FileX example. And again, this example is on GitHub.
And while you're pulling that up, I'll just make a mention of, we'll give you a vanity link at the end that goes to all of these different samples. So if you're frantically trying to write down what the URL is that Scott is sharing, don't worry. There is one vanity link that controls them all, has them all. So
this is a FileX demo, and we basically just create kind of a file system in RAM. So we use a RAM driver. And again, in main, we call tx kernel enter. Our application define is where we set everything up. So all we're doing is just creating a thread here and then initializing FileX. So in this thread, we format our disk. And we're either using exFAT or normal FAT32. And then basically in a loop, all we're doing is opening the disk. We have this optional fault tolerant enabling. So if you actually wanted to test out fault tolerance, this is a good way to do it and just see what's going on in your system. And then all we're doing is creating a file called test.txt and writing, and then we open that file, seek to the beginning of that file, and then we just write the string, the ABCs to the file. And then we go back to the beginning of the file and we read the file and basically make sure we've read the correct data, and then we close the file, and then we actually close the disk, and we just do this loop over and over again. So it's just a simple kind of way to see FileX running.
And then I'm going to go ahead and just jump into the question. With FileX, what if you want to work with, let's say, a USB flash drive, maybe a SSD, maybe a SD card? Is there support there, or how?
Oh yeah,
do you do that?
Yeah, you can use FileX on just about any media out there. So yeah, MMC, SD card,
Okay.
NOR flash, NAND flash, USB flash drives, um, yeah, SSDs. So yeah, if you can store data on it, or if you can store a file system on it, you can use FileX on it. Yeah.
And I can imagine that's probably already in our docs that just got transferred over to the Azure documentation user guides.
Yeah, so all the user guides are now available online. You don't have to download a PDF. Everything's just available online. Um, and I assume you'll provide links to those.
Yes, definitely. All right. Well, I think let's jump into the next component, the TraceX.
Okay, yeah. So TraceX is a nice little, again, TraceX, you actually run it on your host system. So for example, your, Windows desktop. But it provides a nice graphical view of what's going on in your system. So you can think of it as a software logic analyzer. And some neat features, it does execution profiling, so and performance statistics. So you can see how much time you're spending in each thread. You can see how much time you're spending in interrupts. You can see how much time your system is spent idling and just doing nothing, where there's no interrupts or no threads running. It shows the stack usage of each thread, and then it logs all of the ThreadX, NetX Duo, USBX, and FileX events. And you can also create your own custom events, which is really, really nice. So I absolutely love this tool for debugging. And I just wanted to show a quick example. So again, TraceX is available online to download, and it comes with a bunch of example files. So hopefully you can see this. My apologies. I don't think you can zoom. I can't zoom in on this either. So this this is actually the same demo, the same example of the 8 threads running in ThreadX that we saw earlier when we discussed ThreadX. So this is basically a graphical view of what happened there. And so this is just logging every event in the system. And you can also, so this is just showing every event, but you can also view things on like a timeline. So you'll see these events are kind of stretched out. So you can actually kind of look at this timeline and see when everything occurs. I like using the sequential mode. And so let's scroll over to some interesting events here. So this looks interesting. You can see that thread 2 is running. It's basically thread 1 and thread 2 kind of interact with each other. Thread 1 sends messages to a queue, and thread 2 receives messages from a queue. So you'll see thread 2 is doing a bunch of QR, which is queue receive, and then there's an interrupt. It looks like the system timer thread runs, so there's probably a timer tick interrupt that happened. And you can see then thread 3 gets scheduled. Thread 3 does a semaphore put and a semaphore get, and then suspends. And then it looks like thread 6 runs. It does the mutex put, another mutex put, and a mutex get. And then thread 4 runs, and it just goes to sleep, actually, but it was the, let's see. So yeah, after thread 4 runs, thread 7 runs, and it's communicating, or kind of interacting with thread 6. Thread 7 does a mutex get, and then goes to sleep, and then thread 2 continues to receive messages from the queue. And the queue is really big, so that's why you see a ton of these queue receive, and then you'll see thread 1 run. So yeah, it's just a really really useful tool to see what's going on in your system. So I just clicked on the execution profile button here, so you can see thread 0 is hardly running at all. Threads 1 and 2 are mostly running in the system. And then threads 3, 4, 5, 6, and 7 are also not running very often. And then you can see how often interrupts are occurring and see how often your system is in idling. And then next is these performance statistics. So you can see the number of context switches, time slices, the different number of preemptions, suspensions, resumptions, interrupts, and if there were any priority inversions. So if you're trying to debug a really complex or difficult issue, this is a useful little statistics. And then the cylinder is thread stack usage. So you can see kind of the size of each stack and how much each stack has actually been used. So you can see here we're only using about 10% of each stack. But yeah, it's I absolutely love this tool for debugging complex issues and just seeing kind of what the system is doing.
Thank you so much, Scott, for showcasing TraceX. And when going through all these components, I'm wondering, and this is a question that we get a lot, is that before we acquired Express Logic, there was support for all of these different cloud providers, and we still have that now. Where would we be able, if you're an outside developer, maybe you're working with Google Cloud or AWS or other cloud provider, where would you be able to find that information?
Yeah, so we still support all the different cloud providers. We'll drop a link in the description where you can find more information about that.
Okay, perfect. Well, thanks, Scott, for giving that overview. I'm just going to go ahead and jump into where you can see all of these resources and some additional resources on how you can get started with Azure IoT. So a couple of the resources to know about is, one is we have this community where we have folks posting their different projects. It's a great way to reach out to the team, and it's called IoT Tech Community. It's part of the Microsoft Tech Community site. And so if you want to see different blog posts from different folks on Azure side, or even Windows IoT, Azure Sphere, or even if you want to submit a blog post, we definitely want to hear what your projects are. Check us out at Tech Community. It's a great way to have that one-on-one interaction with us and other community members. We also have the IoT show, which I'm going to do a plug there because we do a lot of videos on different announcements. We had the one for Azure RTOS, but we have them for across all of our different Azure IoT services. And next, I would like to highlight that we have the Azure RTOS GitHub repo. That's the vanity link there. So it's aka.ms, AZ RTOS, TAC GitHub is the vanity link that will take you to kind of the main area of GitHub where you can have the see the getting started guides with our different partners. So if you are working with say, the IoT Discovery Kit development board, we actually have a getting started guide with that. You'll also be able to see all of the different components. So all of the samples that Scott showed, if you just go to that one link, you'll be able to see all of that. And we also are showcasing all of our previews, so our public previews, like the support for Azure Security Center for IoT. We do have support for Azure RTOS for that. That's in public preview. You'll be able to find that in the GitHub repo as well. And then something new that Microsoft just released is the Microsoft Q&A. So this is a great place where if you have questions, technical issues, or want to give feedback, definitely go to Microsoft Q&A because we're there, we're answering these questions, we're constantly monitoring, especially for IoT. And we do have folks who are looking at Azure RTOS, including myself and others, who will be there to make sure that the questions get answered. So Again, huge thank you to Scott for giving an overview. I'm really excited for the next round of videos where we'll show how to build it, and we'll go really an extra layer of deep diving into it. And thanks for everyone who's asking questions and joining in. So I hope everyone has a great day, and thanks again.